Good morning, everyone, and welcome once again to the Friday JKMRC Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respects to the ancestors and their descendants who continue cultural and spiritual connection with country and recognize their valuable contributions to Australia and the global society. It's my great pleasure to welcome Dr. Richard Gloaguen. So Richard is the head of exploration department at the Helmholtz-Institute Freiberg for resource technology. He received his Ph.D. degree in marine geosciences from the University of Western Brittany, Brest in France, in collaboration with the Royal Holloway University of London in UK and Göttingen University, Germany in 2000. He was a Marie Curie Post-Doctoral Research Associate at the Royal Holloway University from 2000 to 2003. He led a remote sensing group at University Bergakademie Freiberg in Germany from 2000 to 2013, and since 2013, he's been heading the division Exploration Technology at the Helmholtz-Institute Freiberg for resource technology. He's currently involved in imaging sensing development, data science, and autonomous mapping. His research interests focus on multi-source and multiscale remote sensing using computer vision and machine learning. Today, he's going to talk to us about non-invasive technologies for metal sourcing in a sustainable society, a spotlight on EU-funded projects. Please join me in welcoming Richard. Before Richard comes, I should say that after Richard's talk, we'll have Professor Stephen Markenworth talk to us also about the M4M mining project. Yeah, thank you.
Good. Thank you very much for your kind invitation. And yes, I will go over the EU project we were very lucky to coordinate in my department, and we're still doing. So my name is Richard Gloaguen. So thank you for the introduction. I would just want to say that I belong to the Helmholtz Center Dresden-Rossendorf, and it's part of the association of the centers, research center in Germany, which is the biggest research association in Germany. Yeah, there is a problem with the slides. So I just want to avoid, okay, it's working now. So you see on this slide that it all started about 6 years ago with the first project we coordinated. This project was called InFact. It was quite a large project with about 16 partners with a budget of 5 million euros. And what we were doing there is try to understand how we can improve exploration technologies and at the same time make them more acceptable for stakeholders. And we'll go further with that. Now it's working? Okay. Okay, so I will talk more in detail about Vector. Vector is a project that is just about to finish now. So that was quite a large project funded by the EU. And as you know, Australia can also be part of the EU funding now, and it means that it could be relevant for you as well. So that was a quite substantial project as well. So with about 7 million funding with 16 partners, so quite a large project. And I will go, okay. No, it's not working. So quite large project with 17 partners, as I said. Is it working now? Yeah. Okay. And it all started with some consideration. So the first consideration that, and I will not teach you anything new here in the Sustainable Minerals Institute, we are facing a paradox. And the paradox is that with green energy transition, we rely more and more on new minerals and elements. And it means that in order to sustain the influx of these minerals, we need to mine more. So I guess that is not new, but that's something that is not totally clear for some of the stakeholders in Europe. So to palliate that, the EU created the Critical Raw Materials Act, and you see that what we need is to secure some substantial part of our demand in critical raw materials in Europe, but also through agreements with partners country to get the rest. So it is quite complicated, and we need to deal with that, especially because if you look at the lifespan of a mine, and I will tell you just to focus on the first part of the image, the rest we will not dwell on today. You see that the risk is maximum when you start your project, when you send people in the field for the first time. At the same time, it's where you have the least investment. So what you ask is basically ask prospectors and junior companies with a limited amount of fund to take care of aspects that they probably were not funded for. So which is a huge risk. And in Europe, I'm not too sure about Australia, but in Europe and in many countries, this is the first step in which a project will fail, because then you will never reach your stakeholder acceptance. So the second aspect, which is probably the most important, at least in Europe, if you look on the right-hand side, is basically a measure of trust. How much does the community trust different industry to do the right thing? And you see that food and productions is about 70%, so it's not too bad. You have oil and gas is not too that great, with 33%. So basically, almost no one trusts the mining sector to do the right thing. So if you go and you ask people in Europe, do you want a mine nearby? The first reaction would be no. Even without thinking, is because there is this very, very strong lack of trust. So we can put our hands in the sand and say, okay, we need the minerals, we go. And it happens, what happens, for example, in Jeddah, where there is the largest lithium deposit in Europe. It's a very critical raw materials, but this project has been stuck for a decade now. And you have a very, very strong resistance against the company. So the other aspect you have to deal with is that for about 1,000, also 500 to 1,000 projects that starts, only a couple will succeed into becoming a mine. So it means that if you engage with stakeholders, you have to tell them that maybe something will happen, but maybe not. So it means that you will go on their territories, on their land. It will affect their lives, but they don't even know what is going on. So we need to improve this ratio, and for that we need adapted methods. So here what happens, and I think it's a very nice quote, is that mineral and metal supplies are geologically determined, yet socially mediated. So it doesn't matter if you have the biggest deposit on Earth on lithium, if you don't have the agreement of the stakeholders in order to mine it. So that is something that is very, very important, and it's what we did with a vector. Okay, so the project of the motivation of a vector is to meet the objective of the EU Green Deal. So we need to meet with the expectation. For that, we need to extract these materials responsibly and sustainably. And it means that we must understand the social, environmental, and technical challenge and how they interact. And our idea is to address these challenges by focusing on human-centered solution to ensure the current supply issues. So we were lucky to have a very, very large and competent consortium. So you see that you have mining companies, you have social scientists, you have research institutions, and all together we wanted to try to find a solution. So what we want to do is combine two things and as interlinked as possible. The first one, it's a usual one, is address the geoscience vectors. How can we improve discovery and make sure that discovery will go into something meaningful? And the other aspect, which is less addressed, at least in Europe, are social vectors. Trying to understand why and how people react to mining and what is required to do in order not to make them change their mind, but to address their problems into the way we want to mine. And then integrate everything together in order to have tools and also advice for policymakers. So I will not go too far into the social science because I'm not a social scientist myself, although I find it extremely fascinating and important what they are doing. And I wish someone will be here to help me with that. But those are some of the results of Vector, and I think they are exceptional. So the first one is how to engage with stakeholders, and some stakeholders are extremely difficult to approach because they are not really interested about mining and what's going on. And that is called Green Deals, and it's basically a game. So it's a game that you can use to engage with people at school, at university, in fairs, any person that you see. And it's quite interesting because basically what you tell them to do is make decision based on facts. And the facts are, so either we will increase your production of let's say green electricity and have a greener economy, and we will mine, or we have to make decision and reduce some aspects. And they play with that, and so they learn that we need, for example, rare earths. What are rare earths and where they go? And it's not something that we tell them. We don't tell them you have to think like that. They have this very important step, which is critical thinking, and they decide themselves, is it important for them or not? And I think that is very, very important. We don't want them to change their mind. What we want is just that everyone start to think about it. At the same time, a group was working on developing curricula. So we were not allowed to directly work with children, but we were working with teachers. And here it was how we can improve critical thinking, and that included also raw materials, because there is a very strong lack in the education at this stage about these things. A lot of people do not know what are minerals, why they're important, where they go, and so on. So we worked a lot on policy frameworks. And one of the important aspects we were looking at is at different ways in the future we should do mining in Europe, and looking at business models and how they would be implemented. One of the very, very key aspects of the social science here was to look at shared value. So what we want to reach is agreement. So, and agreement usually in the terms of social science is based on a shared value. It means that together we will get something that is mutually beneficial. So how to engage with the communities and try to understand what they need in order to agree with a common project. So for example, you go to an area where they have a huge problem of infrastructure. So maybe you want to put more effort on that than on something else. And you discuss with the stakeholders in order to get this shared value and have this dialogue, because the dialogue is something that is extremely missing, at least in Europe. Another aspect that was quite interesting as well is that is a game that you can play online. And it shows, so you are playing as a prospector, and you try to see what you need to do in order to get your license in in an area, and you see that it's extremely complicated. So it's a quite nice game. So you see a lot of tools that are based on social sciences that are extremely important for the project. So I guess here you are more interested in the geosciences part of it. So we had 3 test sites. So one was in Jadar in Croatia, so in Serbia, sorry. So the largest lithium deposit in Europe. We could not work there that much because of the situation. So maybe you have heard, it's a very, very complicated political situation, and the EU asked us not to interact there too much. So we used some of the legacy data, but we didn't do that much. So we had quite a big experiment in Spremberg, so that is a copper deposit, and also in Ireland, which is a tin lead deposit. So I will not go into all the results. We don't have time. We have to make an overview. And one I think of the nice results is the deployment of passive seismic or ambient noise seismic. And here, so you see that we deployed quite a lot of stations along the roads to avoid having to disturb too much the landowners there. So that was a test to find out if having a non-random or a non-equally spaced station would work, and it worked quite well. And we compared it with an active seismic cross-section that was performed a couple of decades ago, and we could retrieve the largest structure. So here, the take-home message is not that with passive seismic you can replace other seismic methods, but that before you go with active technologies, you can use that to better deploy your instrument and engage also with the stakeholders. Another aspect that we were working on is developing tools in order to process the data. So there is an open source tool to do geological modeling called GEMPI, and I will really engage you to use it if you are doing geological modeling. So it's fully open source, and during the duration of the project, we continue to develop some of the other tools in this framework. And finally, something that is very, very important. So we developed interactive tools to visualize 3D information. So if you want to discuss with someone and you have a 3D model, it's extremely difficult. And here the idea was to use augmented reality, virtual reality to be able to do that. And if you are engaging with stakeholders that are not specialists in 3D, you can use your tablet, for example, and show that with a tablet, and they can see in 3D what is going on. So I think this has a huge potential, not only for the geoscience sector, but also when you want to engage with different stakeholders, because there you can really have an idea of the scale, where it is, how it looks like, what is going on, where are the boreholes, will it affect us? You can integrate geophysics, you can integrate your geomodeling, and you can start really discussing about what is the reality and not what are perceptions, which is probably the worst that you can do. So an interesting result of the project. So I had to go very, very fast over the results, but I think what is important is that you see the gist of it is the interaction between geoscience, social science, and improve the communication and the engagement with different stakeholders. Okay, so as I told you, so shared value assessment, how can we agree on something that is contentious at the beginning, modeling the subsurface, new technologies, integrating that together, and at the end, improve understanding and sharing this understanding in order to improve the chance of a project to go further. So the final result of Vector was a movie, and I think it's a very nice movie. If you go to the webpage, you can see it. It's about 30 minutes. And here the idea is to using the game I showed you before, with 100 persons that were selected randomly, to try to understand how they react to informations. So how do they react with some facts, and does it change the perception about mining? And the good thing here is what, with more information, they change some of their opinions. Sometimes it was to go more against mining, sometimes it was more against for mining. But at least what we reached is that they were more informed, and that their decision was informed and not just a perception based on suggestions. So quite important. So the second project I want to talk about is a bit different this time. So here there is no social science, but it has a huge implication for the stakeholders. This project is called MOSMIN, so it's not the same, exactly the same format. So here it's funded by the EU, but through another agency, and it's EUSPA, so the European Agency for the Space Sector, something like that. Yeah. And here the idea is to look at mining with a different perspective, is how we can minimize risk of a mine and how we can increase the value and reduce the waste. So we are looking at waste up, we are looking at tailings, and we are looking at stockpiles. So, and here we have quite a few partners, and one of them is located in Australia actually, but here is the assets of interest are in Zambia. But we have a lot of mining companies with us. We have people specialists in radar, people specialists in remote sensing, but and also very, very important, we have people looking at different business models, because at the end of the day, what we want is to produce a product that can be transferred. So, and here what we are doing is also something that is a bit different. What we try to do is what we call a vertical integration. We know that remote sensing will never give you the answer. It can guide you, but it will not give you the answer. For that, we need in situ information, and we need validation. And that's what the industry was, the mining industry was always telling us. If you are looking at the stability of a dam, we need to know. So we not have to guess, we need to know if there is a problem or not. So it means that we need to integrate this information with in situ technologies. So here we are looking at quite advanced technologies. So we are looking at ERT, ambient noise tomography, and DAS. So distributed acoustic systems. It's similar to, it's a kind of, so it uses fiber cables, and you look at the stress on the cable to find out the deformation. So it can give you the indication if there are deformation on your tailing dam, for example. And we combine that with remote sensing techniques. So I will go through a few of these techniques. So here we look at time series. So, and here we are looking at the evolution of a tailing pond in Romania. So that's a tailing pond. And you see that through the years, there were changes. Those are the spatial changes through the years. So we use time series like that. So here you see that's a variation of the vegetation through the years. So we have quite a long time series, and we automatically extract anomalies, and we use this anomaly to understand if there was an event, and we look at the trend to understand in which direction does it go. Is it a positive trend for the vegetation, or it is a negative trend. So here you see that the lake or the pond is growing rapidly, and we can measure that exactly through time. So it's not only important for the mine, but it's also important for all the other stakeholders, for the government, for NGOs, for the local communities, because here you can really show what is going on. Yeah? And sometimes what you realize when you are working with people is that they are talking, but they don't know about what exactly they are talking. So here we have exact numbers. So the same for the evolution of tailings. So you see one tailing in Zambia here, and what we are looking at is a time series of the evolution of these structures, and then you can plot them through time. And here you see that you have the evolution of the pit, the processing area, the tailing dam, and here the waste, and we can see the evolution through time. So it is important because we found out with many companies actually that they don't know. Sometimes they don't know where are their waste, what kind of waste they had, because it had gone through different management, they lost or they didn't really look at it. And just a couple of weeks ago, we were discussing about that with the company, and they told us they would be extremely interested to find out where are the waste, because they have, or they can have an impact on the environment, AMD, for example, or they could have value. And for that, they need to know where they are. So here you can monitor this as well. So that is an interesting result. So you see here it's in Chile, and you have a tailing dam, and they know that it is at risk. They have observed a few things on it. So we are looking at SAR interferometry to look at this displacement. So I will not go into detail, but just know that with this technology, we can measure displacement in the order of sub-centimetric displacement. So we can do that. But sometimes it's difficult to have a very, very wide area of information, and you want to have certainty. So what we developed, what we put on the ground are these ground corner reflectors. So the SAR is emitting a signal. It will be reflected to this by these reflectors, and it will be very bright. So you see those bright spots here. So those are the corner reflectors. So they are just 1 meter wide, but you can see them on a pixel that is 30 meters wide because they are so bright. And because they are so bright, they will always be there on an image. So it means that on this corner reflector, we can have time series, and that will be in the millimeter range. So we will know with millimeter accuracy what's going on, so we can know what the displacement on these dams are. So very, very important, but it's not sufficient. So we need to have certainty, and that's the reason why on this tailing dam, we have also geophysics. So we have these fiber cables, as I told you, but we have also ERT. So we have electric methods in order to find out really what is going on the subsurface so that we can link the two. So that is what I told you, the DAS. So that is a long cable, it's a long fiber cable. And every time the cable is under stress, it will modify the signal that goes through. And we can know not only the amount of stress, but also the location of the stress. So it means that we will have a very precise information of the displacement on this dam. So it's quite easy to deploy. It's not a costly technology. Extremely robust, and in combination with remote sensing, then we get a very, very good understanding of what's going on. So we can, from space, identify different type of rocks. So that's an example in Finland, and that is the tailing of a phosphate mine. And we found out that in their tailings, they have rare earths. So that is value. And if you can identify and quantify this value, you can help the company to use this information in order maybe to process these rare earths. So we know that the company here in this case for unique is still in Järvi, so so they are looking at different options, but that I'm not sure how far they are on that direction. And the last, which is also important, so the risk. So here we can measure some parameters that are directly mapped from space on the concentration of different elements in the rock and predict acid man drainage, for example. So we can look at the potential for acid man drainage, and we can now look that through times because we have satellites that will again and again acquire data, which was not the case in the past. So what we do is not only do it just from space, we calibrate and validate this information with in situ information, so to make sure that what we are predicting from space is accurate. So those are the different results of the project, but what we want to do is to put everything together. So we develop a platform in which all these tools will be integrated. That could be used directly by the companies, that could be used by the different stakeholders to visualize all this information, but we want also to develop businesses with that. So that is another approach that we are looking at. So I think I give you on time a good overview of what we're doing with this EU project. I think what is also important is for you to know that the EU has identified a few countries of interest to have this strategic agreement to secure the supply chain, and Australia is one of those. So you can be pretty sure that in the future there will be calls that directly target Australia. And Steve, we will show you exactly one example of those.
Thank you, Eric. And how do I navigate? Oh, yes. Okay. Hopefully you can all hear me online. So Richard's done a great job describing some of the large-scale initiatives taking place that are very relevant to our work here at SMI across Europe. And as he's mentioned several times, in Australia, Europeans consider us key partners. And so there's opportunities for us to collaborate very closely with groups all across Europe to achieve many things for the resources sector. And this is an example of one of those. This is Project M4 Mining, which is a little bit more granular in detail than the projects that Richard has been describing. This project is all about developing a new generation of hyperspectral imaging tools from drone. And the key thing really is developing the ability to image landscape with hyperspectral sensors and deliver analysis-ready data in real time or near real time. And for anyone who works with satellite data or with hyperspectral data, they would know that that is quite a challenge. Now, we only have limited time, so I'm actually going to flick through a lot of slides quite quickly and try and get to a video which sort of summarizes some of the most recent innovations. But this project will actually come to an end in the end of 2025. So we're very, very close to fruition. I'll be going to Germany for the end of project symposium in September. And here at the University of Queensland, we've already bought a beta version of the tool that we've developed within this project. And we will hopefully have some of this capability with us. Well, we already have this capability with us, and we're getting trained on that slightly later in the year. But that slide there is simply to illustrate the sorts of ranges of applications you have the potential to apply drone-based hyperspectral and satellite-based hyperspectral imaging too across the resources sector. So you can see there's a large range of applications. And as with Richard's projects, large number of partners, European-led, and a total funding of up to just over 4.5 million euros. In Australia, we actually received around 400,000 Aussie dollars for the work that we've conducted. And this is the team on our end. But what I really wanted to illustrate here, the list of names on the left there are all participants from SMI who are involved in the project. But at the same time, as this project's been running, I've been able to establish what's known as the Drones Collaborative Research Platform, which is centralized drone-based infrastructure. And that's an ongoing facility that industry, government, and researchers can access to be able to get their hands on these toys, get their hands on our expertise, and do a lot of the work that Richard's been talking about and which is illustrated in this talk. And yeah, I won't go into that detail, but yeah, we've got a few nicknames floating around. Very briefly, it's not just about the drones. And I think Richard did a reasonably good job of also illustrating that this technology only works if you're vertically integrating it. So in this particular project, we've been developing the drone technology, but we've also been exploring, well, how does the data that we're collecting compare to well-established, robust satellite data? And can we begin to think about ways we can integrate those two scales of data set much more seamlessly? So down to the key results. What you're seeing here is a slide that illustrates that we are now collecting LiDAR data and meshing it in real time, which is the image on the left, and then projecting over that the hyperspectral data that's corrected and has taken into account all the geometric and atmospheric effects that can degrade hyperspectral data. And so we're now at a point where with some software tools that we've developed within the project, and we've also taken advantage of that were already in existence, we've now got that working, or almost, I'd say 90% of the way there. And I think on the next slide, we have a video.
All of this happens without rapid feedback, meaning you're not adding any unnecessary overhead. It's all about delivering the results instantly. We believe it's groundbreaking, and it will completely transform the way hyperspectral technology will be used for real-time applications. Picture this: you're collecting 500 megabytes of data every second from a drone, and instead of waiting hours or days to process the data, you're now analyzing and using that information on the fly. The possibilities are massive. For industries like mining, it's game-changing. Imagine being able to instantly identify mineral compositions and environmental changes. But the applications go far beyond mining. Agriculture, environmental monitoring, defense, forestry, the potential is virtually limited.
Great. That was Agnar, who is absolute joy to work with. I'm actually going to leave the talk at that stage because we want to have lots of opportunity for questions that you might want to direct to Richard. But I think that really gives a flavor of what we've been doing in M4 mining and the context of the work that we hope to do in the future with our European partners.
All right. Thank you very much, Richard and Steve. Any questions?
I have a question about, so you showed an image where you had the reflectors and you talked about 30-meter pixel size, but then you talked about millimeter precision in the data. So I was trying to work out how that millimetre precision was actually displayed with respect to the 30-metre pixel size.
Yeah. So that relates to the SAR technology actually. So you don't get 1 millimeter precision of the pixel directly. You get a 1 millimeter precision on a time series. So you will not get 1 millimeter directly if you do one measurement, but because you have a lot of measurement, then you can measure the evolution. And that's true. You don't need 1 millimeter precision for one pixel in most of the time, but sometimes you are looking at buildings or dams or whatever, and in this case, it can be really, really important to have this precision. For mining monitoring, I think if you are 5 millimeter or 1 centimeter, it's already okay to have this precision. But technically, with INSAR, you can go up to 1 to 3 millimeters. Yeah. Yeah.
So the size of the data set is spatial resolution for the pixels is 30 meters. And is that just spatial information from the INSAR data, as in elevation of the surface?
Yeah. You get what you get is the displacement in the line of sight. So the SAR is looking sideways, and it's basically it's radio detecting and ranging. So it's precise within the wavelengths, or a fraction of the wavelengths, and the wavelength is usually a couple of centimeters. So you are precise within that. So you have ambiguity usually over this wavelength. So you don't know if it's sometimes you don't know if it's 2,000 kilometers or no 800 kilometers and 2 centimeters or 7 centimeters. But within that, you know the displacement. So if you put that on a time series, then you will be able to measure the displacement extremely correctly. Yeah. So you have an altitude of ambiguity, but you can resolve that.
Going, my name's Andrew from Communications here at SMI. My question kind of tries to combine the two projects. So do you feel that having better imaging and having these models that people can move and touch and those kinds of things helps to build trust because they can sort of see it with their own eyes rather than having to take our word for it in terms of, you know, what the impacts will be?
Yeah, so in the geosciences, people are very familiar with maps, with 3D visualization, but it's unique. So most people are extremely have difficulties to understand what are the spatial relationships, especially when it goes to depth. So what does it mean? So if you can show them what it means, where it is, yeah, because the question is, will it be next to my garden or 2 kilometers from my garden? How deep will it be? Where will be the waste dump? What will be the impact with noise, with dust? And if you don't have really a very clear spatial knowledge of that, you will be suspicious. That's one thing. The other thing is that it's not only that you can see it, but those are data. So you can really show the data, and you can also help to monitor and try to understand what is the influence through time. So is it polluted? Is it not polluted? Do I affect the forest or not? So all this information I think is important. So what we say is that you should have informed and prior consent. So, and if you have that, so it's a good way towards trust. Then you need less to have this kind of interaction. But first, you have to demonstrate that you are doing the right thing and the willingness to show all the data in a way that it is comprehensible. Because I can show you a table, for example, I could show you a table of results of DAS, and even you, as a specialist, you will say, nice, but what does it mean for me? Yeah, so you have to transform that in something that is understandable to the stakeholders and all the stakeholders.
Thanks, Richard and Steve. I don't know which of you want to answer this. Looks like you've kind of solved everything, at least from an ignorant, non-specialist point of view. And I'm sure you haven't, because there's always more to do. So what's the next big thing? Is it just improving the resolution of these tools? Or is there some big black hole which still needs to be filled?
Yeah, I think that's a very, very important question. So it's like what you are doing, all of you. It works in the lab, yeah. And then you go and you scale it up and you realize that, oh, we forgot about that. It rains, or there is too much wind, or there is that and that. And it means that I think what is always missing with research project is how to make it operational and adapted to the person or to the user. All the mining companies told us, it's nice that you have that, but how can I use it? Yeah, I need to put it in my workflow and it must work. And right now, that is not the case. So we are looking at make it operational. So Steve showed that, yeah, so it's in real time already. So it means that the people on the mine will get the results. That's one aspect. But the other aspect is also to get them the data in the way they can use it. So, for example, if you look at spectral information, if you give them a spectral map, and they will tell you, but okay, I need to hire a spectral geologist to understand that, to put that in the workflow, to discuss with my, it's not what I want. What I want is give me my minerals or give me the information I need. And that is something that we need to work on. So I think we have quite a lot to do down the line. So the operationality is very important. So we always show drones flying where it's nice weather and it's sunny and you see people in shorts and flip-flops. Nice. But if you are in the north of Finland, it will not be so easy. Or if you have really strong winds, if you have vegetation. So it's flying with a drone when you have trees that are 40 meters high is it's tricky, yeah.
Sorry, I got there. Come on. This is sort of a two-parter. The Kupferschiefer is, one of the oldest mined copper belts in the world, and it's got some very, very high-grade deposits in it. Firstly, do you think there is exploration, or is exploration being done there? Do you think is there potential for discovery in that belt remaining? And if you did discover something, do you think there is enough support culturally, as you were looking at in the Vector project, to actually permit a mine somewhere in between Germany, Poland? I don't know, does it extend to as far as the west of England?
Yeah, my first reaction is ouch and ouch. Because, yeah, so people know, yeah, so you can follow the Kupferschiefer. So you have two things. One, is it economically rentable? So it goes deeper and deeper. So here I think it's 600 meters, something like that. So 400 to 600 meters. Oh yeah, okay, 1.5 kilometers. So even if there is something, it will be difficult. There is exploration, so you have at least two explorations. So, and even Anglo-American is doing exploration there. And in Poland is, but it's much shallower. And yes, you are right. To gain acceptance will be extremely difficult. Here, in this case, in Spremberg, they are using the fact that actually they will mine below a coal mine. So the people around it are familiar with mining. They live also from mining. So maybe there is more acceptance in areas like that. It actually is one thing that we are trying to focus on in the future, is to go to areas with with historical mining, because there the people know there are also infrastructure and so on. So it's one of the projects that Sam is working on actually, to have that kind of brownfield exploration and not to go too far, because there is no pristine areas in Europe. Everything has been used, so you have either forest or habitats that are extremely important. So you have always a frog or butterfly that will be difficult to displace. So yeah, you are right.
So I worked for a while for a lithium junior, doing experiment development, kind of on the left side of one of your early graphs there. And we used to talk about, we get the projects to the point where you're trying to cross the desert for funding, and there's a lot of skeletons in that desert. Now, our projects, I think, face more challenges that were technical. And I know a number of other projects that eventually failed were more around technical and financing. I was wondering if you could comment in the EU, kind of that split between projects like YADAR that face significant social and environmental, kind of ESG problems, and other projects that might fail. Just what's the ratio there in terms of why some of these projects aren't making it through the pipeline into production?
It's a very difficult question, and I'm not sure if I'm the right person to answer. I would make the distinction between two things. So if you are in countries where your GDP is really depending on mining, then probably you will have less problem than in other countries. But for Europe, beside the south of Spain and Finland, it's a nice to have, but it's not something that people are aware of. We are working with the car industry, and they say we will get our minerals. Yeah, so far, okay, we pay a little bit more or less, but yeah, so that's not really the problem. They only start to really care about it when there is a shortage. And then it's panic, and you see that it flips almost on a daily basis, yeah, so it's very difficult. Concerning the technical challenges, you would have to tell me exactly what are the technical challenges, because I cannot really answer that. Yeah.
A question from one speaker to the next. So going back to Tom's point about the Kupferschiefer, it does actually extend to West England, yeah. And well, we're not sure, but anyway. But what's one of the things we've done in northwest of England is just recently put down an underground mine that goes beneath a national park, and it's mining higher, I can't remember the name of it now, a type of salt for fertilizers. No, not potash, no. Anyway.
I heard about that.
Yeah. So, that from a community perspective, that's been accepted, and it's had very little in the way of significant opposition. And the main challenges to that project are now actually financing and things. So my question actually is, in your social work you guys have done, have you come across a difference in perception of say, underground mining versus open pit mining, and how people, low footprint operations versus operations that might be having a larger surface impact?
Yeah, so I would say that is secondary and far after trust. So I can give you a counterexample. So in Sodankila, you have Sakatti, and Sakatti has exactly the same problem. They are exploring on a Natura 2000 protected area, and they say that they want to have a tunnel 7 kilometers wide and go down and so on, but they have a huge problem of resistance by the indigenous people, but also within entire Finland, because no one trusts them that it will not affect the water table. So I don't think the case that you were mentioning is indicative of everything. Even if it's underground, it will not help. In very near to where we are living in Zinnwald, it will be the same. And the people ask, but where will be the tailings? Will we have collapses? So it's a very tricky question. And so far, we have not found really a direct link between underground or pit. So it's true that when you talk to people, they always say, oh, there will be a huge hole in the landscape, and that is horrible. But at the end of the day, when there is a project, it's more complicated than that.
Yeah, that's great. Thanks, Richard.
We'll take one last question. Okay. If there's none, I'd like to thank Richard and Steve again. So please join us next week. Next week we have Tanya from JKMRC talk to us about soft sensors for mineral processing. Thank you for coming.